Okay, so let's say what we mean now by what it means to be integrable, or the integrability of a function. So we defined a upper integral of f on a partition. Let's define an upper integral on the entire interval now. So we've got some definitions. So we're going to define the upper integral from a to b of f of x dx. That's going to be the infimum, even though it's upper, it's the infimum of the upper integrals on a partition P of the function f over all partitions of P. Okay. Remember, when we refined a partition, the upper integral on that partition got smaller. So this infimum is the smallest that you can get, no matter how refined that partition can be. And we're going to similarly define the lower integral from a to b, f of x dx, equal to, well, when we refined lower integrals, they got bigger, so the supremum over all partitions of the lower integral of p on f. Okay, so as we refine things, the lower integrals get bigger, the upper integrals get smaller. These are the bounds on how small the upper integrals can get and how big the lower integrals could get. And these are good estimates for what the area under the curve should actually be. And when it exists, they're going to be equal, and that's how we define the integral. So if the lower integral from a to b, f of x dx, equals the upper integral from a to b, f of x dx, say it's equal to I, then we say f is integrable on a b, and the integral from a to b, f of x dx equals I. Okay. This sort of means that there's some functions that we can't integrate, and there's some functions we can integrate. So let's see a couple examples of those. Let's see sort of a silly example first. Let's just look at say f of x equals the constant function on AB. Then for any partition, m sub I equals little m sub I equals c. The maximum values in any interval and the minimum values are all the same. And so the lower integral of that partition of f is equal to c times the difference between a and b. If you don't believe me, you can go back to that summation formula and add it all out, and you'll see the inside points in the partition sort of add and subtract, and it telescopes down to c times b minus c times a. And it's the same thing as the upper integral. So the integral of c dx from a to b is equal to c times b minus a. That's an integrable function. Every constant function is integrable. Okay, let's look at a non-example now. So this is one of our pathological functions from a while back that we've used a few times. So it's going to be 0 if x is not rational, and it's going to be 1 if x is rational. Oops, is rational. Okay. Then, given p, on any interval between xi and xi plus 1, there are going to be rationals and irrationals inside this interval. Okay, that means that m spy is equal to 1 then, and let me put a so there, and little m sub I is going to be 0. Okay, this gives me the upper integral on the partition of f equal to b minus a, whatever b and a were, and the lower integral is going to be 0, right? So the upper integral on the entire interval, this is just a constant, is constantly b minus a, so the supremum is b minus a. And that's not equal to 0, which is equal to the lower integral from a to b, f of x dx. So f is not integrable. Okay. So here we had problems because of discontinuity, and it wasn't just that it was discontinuous at a few points, it was sort of discontinuous everywhere. If it's discontinuous at a few points, we can kind of fix that by putting those points inside the partition, and then we can kind of avoid dealing with them by making where we're looking at those discontinuities really, really small. But if it's discontinuous sort of everywhere like this, we have some issues. Okay, so I need to do a little bit more topology, but we're going to see that if f is a continuous function, it's on a closed interval, it's going to be integrable. In the next video I'm going to talk about uniform continuity so that we can prove that theorem.